Hello and welcome to TidyX episode 60. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick. And TidyX is on Twitter at Tidy_explained. TidyX is also at Gmail at tidy.explained@gmail.com. Or like and subscribe on the YouTube channel, leave a comment, or open up an issue on the GitHub repo. And TidyX is 60 years old today. So
Wow. How did that happen? I don't
I
how did we
know.
get to episode 60 already?
Um,
I guess we've done 59 prior episodes. So.
Yeah, and a global pandemic has substantially focused our attention on other things. I guess
Exactly.
There's less areas where we could be doing other things in our life, I guess. Yeah.
But yeah, no, we're really happy to be here at episode 60. We nearly have 1,000 subscribers, so this is awesome. Thank you all so much for being here over the last year plus. As we've recorded these, and getting feedback from you all has been wonderful. We actually had somebody open an issue this last week where they took the series that we've been doing on PitchF data and applied it using tidy models. And they recreated what we did, and it was so cool. So we're hoping that we can highlight that a little bit later on.
Yeah, awesome.
Because we love user contributions. So definitely share that. All right, Patrick, what are we doing this week as I share the screen so you can see what we're talking about?
So we've probably done 7, 8 episodes now with this PitchF data, courtesy of the MLB game day package, which makes it super easy to scrape PitchF data. And our goal has been to classify pitch types based on a number of features. So there's 9 different pitch types, and we're classifying based on a number of PitchF features, so the movement of the actual ball. Mm-hmm. And as always, we throw up some quick resources that are useful if you want to understand PitchF data, or if you want to use the MLB game day package, which is, again, super easy to use and super useful. But now that we've gone through about 7 weeks, we've created, I don't even know how many models. We've gone through lots of different model types and machine learning models and things like neural networks and things like that. So you review those if you're interested in that kind of stuff. Today, it's time to get down to brass tacks and compare these things and see which model would we want to go forward with, or maybe think about ways in which we can improve things. But this is the last model in the series. We're going to put a fork in it. It's done. And we're moving on to something else.
Moving on to greener pastures.
Greener pastures. So let's compare models.
I'm sure you all are tired of hearing us talk about PitchF. All right. Yeah. So we're going to quickly do some setup here. So as always, setting our path. So BP is our base path. Setting options here. We're loading a ton of libraries, but this is because we have a ton of models that we're training this week, because it's all the models we've done over the last 8 weeks or so. So we're going to load all those in. Then we're going to set the plot theme to theme light because we just like that. So let's just run that there.
I don't even think we have any plots this week, but
we don't. We could have. We thought about it. I know I thought about it, but ended up not doing it. All right, now we're going to load up the data that we use to train all our models. This is what we did in episode 53. You can check it out at bit.ly/TidyX episode 53 for all the details on that. But as we've been doing, we are skipping forward to the next piece. All right. So we have a ton of models to train, and we could manually go through and edit each one and type it in and have a ton of code and be really long. But what we decided to do instead was take a more functional approach to this, rather than spending a time and copying and pasting literally everything that we did over the last several weeks. I wanted to maybe take a second to go, here's how you might approach if you didn't have something like Tidy Models or something like that, which is an awesome package. But you just wanted to quickly kind of iterate over different functions in models and whatnot and then summarize all the results for us. And so here we have a bunch of the way I like to organize my RMDs and whatnot, have all my helper functions towards the very top. So it's easy to scroll up and see where they are, and they're always defined very early on. So you have access to them very early in the processing. So we have this function here called model summary. Its purpose is to simply take the output model and grab some basic information for it that we're going to be using for our evaluations, because I don't really want to keep the full model necessarily for my evaluation piece. So it grabs the model, the actual classes, so the actual values of the data, the probabilities from the output or from the model, the predictions of the class from the model, and then we have this param argument there that is going to take a list that all the special things that I'm using to define my model. So like in random forest, it's the mtry that we use is param. So I'm using that just to track that in future in case I want to come back and rerun that. And I'm creating a special S3 object using the structure function. What this means is that now I have an object with class fit model outputs. And now I can go through and I can write methods, so write functions like print, and say, okay, print fit model outputs and have it print in a special way. I didn't do that this time because it's not super useful, and really the reason I did this is that I've been developing a lot of packages lately and my brain just kind of likes this. So I like S3 objects a lot. So now we have a bunch of functions here that are going to be helping us manipulate our data. We've covered this in several different episodes. Like in episode 54, we did a bunch on scaling our data, which is making sure that we essentially apply a z-score to all our data, but we do it based on our training data so that our test data, our model is trained on training data, but it only knows that values, and so we need to use that to then scale our test data. It's a little confusing. Basically, we don't want any information from test to make its way into the training. Right. So we have this function data scaling, so it takes in the train and test data and applies what we did in episode 54 to scale our data for us. So I'm not going to go through this as well. If you want to learn more about it, look at episode 54. Same concept here. I'm going to be manipulating my data, but this time I'm going to be downsampling it. And so we covered downsampling in episode 59. It's a bit shorter of a function. Really all it's doing is applying the downsample from caret to this and then reassigning the name class to pitch type so it remains consistent across everything. So we do have our downsample, upsample, same concept, but we're upsampling from using the upsample function from caret. And now we have a bunch of evaluation metrics here. So this is the ways that we're going to be looking at the performance of our models so that we can empirically compare them. So we have our accuracy, which is the same thing that we've been doing over, like at a high level when we look at our models, we look at overall accuracy and then within class accuracy. So this function takes x, which is expected to be a object of class fit model outputs, and then simply calculates the overall accuracy. So the number of times we're right. So the number of times class actual is equal to the class prediction divided by the total number of predictions we made. Within class accuracy, same thing that we've been doing as well, looking at the actual class prediction and the actual class and the predicted class and figuring out how many times we're actually correct within the correct class. Bit circular there, but boop, boop. Then we're going to look at different ways that we can look at our models as opposed to just accuracy. So one of them is log loss, which we covered last week in episode 59. Applying that same multi-log loss here, there's some setup around here just to make sure that things are formatted properly. There's nothing really special about this other than formatting and returning then the multiple log loss. We have our multi-class Briar, which we also covered in episode 59. Same little setup here, just make sure that the column names are as we expect them to be. And then finally, AUC, which is calculating our AUC, which is based on the ROC curve, which we also covered in episode 59. So watch our last episodes if you want us to go really more in detail about what these mean and how they work. But it's just different ways that we can look at how closely accurate we are, or what is the overall power of the model. It kind of, and then finally there's the summarize models here that's going to actually apply all these evaluation metrics for us and return a nice tibble, because I'm lazy and this was easier than copying and pasting a bunch. Essentially, I mean, when you write a function, essentially you're copying and pasting, but making it so rather than you have to do Control-C, Control-V, you just type in the function name. At least that's how I like to think about it.
Yeah.
And so we're going to, takes in a list of models. Over these list of models, it applies all these evaluation metrics and returns a tibble. And then binds some information like the model type and some information around the model, like did we optimize it or not, and then the data type. I know the order in which these lists are coming in, which is standard, upsampled, and downsampled. Cool. Alrighty. I've been talking a lot. Patrick, do you want to take us through a little bit? Like, we'll just go through one, but all of these are identical.
Yeah, we essentially did this. Basically, these are the steps that we ran for all the previous weeks whenever we talked about a single model. So I think actually after our initial data exploration, the first model was KNN. I believe you have these set in the order that we did them in. Yes.
Yeah. Tidy. And then if you look at the code here, I'll have the episode that we talked about the model in. So if you want to, we're once again not going to go in depth in the specific models. But if you want to learn more, we do in the actual episode.
So taking the first chunk here, looking at KNN, K-nearest neighbor algorithm, you could see that Ella starts the chunk out there with that little eval argument up at the top right there. So basically what that's saying is eval exclamation. So remember, exclamation is like saying is not. So eval equals if this file that's being produced in this chunk, the file that's going to be called knn underscore standard underscore models dot RDS. So he's going to write this out to an RDS file. We've done that a ton throughout this series. So you can see that in previous versions of the series. It's saying if this file doesn't exist, when he knits this, it's going to say if this file does not exist, go ahead and run this chunk. But if this file does exist within our working directory, don't run this chunk, don't waste your time, move along, nothing to see here. So he's written a function here, and as he said, there's going to be a function for every single model that we've done so far. This one is going to be called model KNN. All the other ones are going to be called model underscore insert name of model. So the function obviously is going to take in our train and our test set, as well as utilizing that helper function that's going to prepare the data by taking the mean and standard deviation of the training set, the population that the model is built on, and utilizing that information to scale the test set, the data that the model is going to be tested on or validated on. Okay, so then we go through and we say, okay, if is null, so if is null data prep function, so if he didn't write anything in the data prep function there, list scales, right? He puts in this nice little for loop here that says for function IDX. So that's basically the ID that he's going to use in the for loop in sequence along data prep function. That's going to be the sequence that he's running the for loop over. He creates this function, or creates this variable output called dat, which is dat prep function. So basically, if you left it null, what he wants to do is go ahead and scale it anyway.
So what this will do is,
if you left it null,
if this is null, don't worry about trying to do anything to the data. Use train and test as it is.
Oh, as it is. And
then,
so maybe, so if someone had, in theory, already scaled their data, they could just say, just null this. I already did it. No problem. Blah, 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 blah.
Yes, exactly. But here, then you can put in a series of transformations you might want to do to your data, and it'll loop over each one of those. So by default right now, what it'll do is it'll just apply the scale data function to it, which is scaling, but you can do...
But you could have done like a min-max scale.
Mm-hmm.
So
you could write a different
output
function.
Minus min divided by max minus min. And you could put that in there in theory, and it will min-max scale all the variables within your data.
Yep. Exactly. And so this is just, it allows me later on to use the same function when I want to do up or down sampling to my data. And so we can talk about that in a second.
Okay, so then this is all just standard fare. He's actually going to run the model. So he's going to use the KNN function right there. Obviously, the KNN function is incredibly intuitive. You pass your training set, you pass your test set, you initialize which class you're trying to make forecasts on, which in this case is obviously the train set with the pitch type. And we used 4 nearest neighbors, which I believe we settled on 4 from the first video in this series, which would have been TidyX 53, where we did all of our exploratory analysis and our clustering and things like that. The outcomes here, he's going to obviously, so the first function, helper function that Ellis wrote all the way at the top called model summary, it basically went through every one of these models and said, hey, grab the model, grab the class that's being predicted, grab the probabilities that are being predicted, and then grab the actual class, what was actually observed. And so the reason for that is if you watch episode 59, to do AUC, you need the actual prediction. You need to know whether you had a hit or a miss. To do the other type of model comparisons that we're doing, like a Breyer score or a log loss, you need the actual probabilities. KNN is unfortunately the function that we use. It's the KNN function doesn't produce probabilities of the outcome classes. It simply says if I thought it was an FF, if I thought it was a 4-seam fastball, it's a 4-seam fastball, or that's it. And then it moves to the next line. So that's why probability here gets an NA. There is no class probability that's projected from that function. Mm-hmm. But that model summary function that he calls at the end, where he goes #return. This is what he wants out of that model, out of the data. So he's feeding the data in, he's scaling the data, he's running the model, and he's saying, okay, the things that I need to know in order to know if this was a good model when I compare it is I need to get what the observed class outcome was, so test $pitch type. I need to get the probabilities of the projected classes, and then I need to get which class was the highest of those probabilities, which is going to be generated as the class being predicted. Yep. And so that's what we get. And then that gets applied exactly to all of the other models. So after he creates that little function, he's going to apply it to our standard and our upsampled and our downsampled data. Remember, he does it in that order because that's the order of that last helper function that he wrote. He knows they're going to be coming in that order so that things don't get unshuffled. So he's going to run that model KNN, which is going to take the clean data, take the test clean data, run the data prep function, and grab those key variables that we need. And then he's going to put all those things into this handy dandy list. So it's a convenient way to store all the outputs. And then let's see. Okay. And then he's going to apply the other helper functions and basically saying, hey, take that list and go ahead and do the overall class accuracy. So how good was the model overall? How many hits did we have? And then the within class accuracy. And then save it as an RDS. Yep. If that RDS already doesn't exist within our working directory.
Yeah. I was doing this mainly just to look at it as I was building everything, because it can kind of be boring just to look at a computer screen just running code and not actually outputting anything. And so here was a way for me to kind of look and see how it was performing just out of curiosity. There was really no need to run these yet.
And so the walk function, as opposed to doing like apply over the list or something like that, apply over the list or something like that. What?
Yeah. So walk comes from the per package, and it's really nice for running code where you only actually want the side effects. So you don't actually want to get a value directly out from it. It's that you want a plot produced, or you want, in this case, really what I was doing is I was just printing out the values that came out of eval accuracy overall and eval accuracy class. I just was wanting to look at these values. I wasn't going to be assigning it anywhere. I didn't want it to do anything special.
Yep.
And so walk allows you to do that and not have to, like if we were to do an apply or a apply or a map, I'd then have to do, and I didn't want to keep the outputs. QUI. I'd have to do that.
Quiet.
Just to like make sure that nothing got assigned or printed randomly that I didn't want to.
Got it.
And so walk is essentially that, but nice. nicer.
Got it. Okay.
Yeah.
Cool.
So then I saved the standard. So I called this standard because we didn't apply any special stuff to the model itself other than the parameters that we passed to it. So I called that standard. And then we do the exact same concept here, but this time we're doing the KNN using caret. This is from episode 54 as well. So we're not going to go into detail there, but as you can see, I tried to format them the same way.
Yeah.
So that they take in the train and the test and then some sort of data prep manipulation all the way through. And that way it was really easy to zip through all the different models that I had and just have to change these guts here whenever I wanted to do a new function or something like that. And then I save that as KNN caret models.rds because this is KNN, but it's based on caret, which is optimized.
Yes.
All right. And then we do the same thing for random forest. Let's not go into any of these because I don't. Leave a comment if you want us to go into more detail on any of these items. But they are
we hashed them out pretty detailed in the corresponding episodes in terms of, hey, here's how you run it, normal standard style, and here's how you optimize some of the parameters within the model, sort of pull the levers and push the buttons of the machine learning learning models, right?
Exactly. But all of these chunks are formatted exactly the same. So everything we just explained for KNN is applicable to all these other functions. I mean, there's going to be slight variations because the models themselves are a little bit different in the way that you pull out information. But we pull out the same exact information.
Yes.
And so we've got, XGBoost, we've got naive Bayes, episode 57. We've got a deep neural network. And then I did add, when we did the neural network episode, we only did one neural network. Here I did add another neural network. So this first neural network here, the NN standard models, that is using what we talked about in the episode, which was, I think, 2 hidden layers with 200 hidden nodes or something like that. Actually, we can take a quick peek. 128 nodes. I did make for giggles a deeper model. So this is 3 hidden layers with 500 nodes, just to give an example for when we're looking at all the models together, how that can impact the effectiveness of the model itself. All right, so we now, through the magic of cinema and screencasting, we've already run all these models because it took me about 5 hours to run all these models, and I don't think you want to sit here listening to us make jokes for about 5 hours. I don't think that would be the best use of your time or our time.
True.
So I've already run all these models for us, and so now we're going to go through and pull all the evaluations and look at the summaries of all the models. So first we're going to use list.files and pass. So list.files allows us to list all the files that exist based off of a path and some sort of pattern searching. So I want to get all the files that live inside the BP path, which is our current working directory here. So Tidy Tuesday Explained 060 MLB Pitch Classifications episode 8. But I only want to keep files that end with models.rds because that is what I named all the models that I created, or all the RDS objects that I saved the models in. So we've got nine RDS objects that we're now going to read through and pull and evaluate all of them very quickly, relatively quickly. For each model, I'm going to quickly print the name so that I know where I'm at in the loop. So model list, map DFR. So we're going to end up creating a data frames binded together by row. So I know where I'm at. I'm going to print the file name. I'm going to separate it out by underscores. So that way I get the model, whether it was optimized or not, and then this is just so that I could search for it later on. So we're kind of throwing that away. So we're going to read in the RDS object. Then we're going to throw it into the summarize models function, which I explained earlier. Basically, is just applying all our evaluation metrics for us and returning a nice tibble. So sorry, kind of going at a high level. Helps if I run everything. Sorry for...
Haven't been running it as we go.
Yeah, I know. All right, there we go. All right, so now let's run that. So now what it's doing is evaluating all our Bayes standard, now our can and carrot models, now our can and standard models, now our neural network deep model, which was the 500 layers, well, not 500 layers, that'd be a lot. 500 node, 3 layers, the RF carrot, and all the regular downsampled and upsampled models for us. And so in a second here, we will have all of the evaluations for all the models we took many hours to run. There we go. We've got it all. So let's take a quick peek at model summaries, which is a tibble that holds all our information here.
Yeah.
So as you can see here, we've got model type Bayes. It was because alphabetically it was the first one that got ran. It's listed first. Optimized is standard, so that means we didn't run any optimization for it. We didn't have a carrot package or something for it. What data type was it? It was standard, which means that it was just the raw, quote, raw data that we just threw at it. Of course, I think for Bayes we did do scaling, I think. Do we scale for Bayes?
I don't think... I can't remember now.
I don't know. But we did like the what you need to do. That was it.
Yeah, I can't recall.
And then upsampled is the upsampled data set, and downsampled is the downsampled data set. So then we end up with the overall accuracy of the model. We have an entry that is a tibble that contains the class or within class accuracy.
Yeah. So there's 9 by 4, right? 9 pitch types. Isn't that what? Yeah, 9 pitch types, right?
Mm-hmm. Then we have the log loss, the Breyer score, and the AUC for all the models that we ran. So we have 27 models that we ran, which, how did we get so many?
Right.
So what we're going to do is we're going to separate out, because I kind of want to look at the overall performance of the model separately from the within class performance. And so we're going to take model summaries. We're going to only select out the model summaries that describe the model overall. They don't actually look at the within class performance. So really all we're doing is removing accuracy class field.
Yep.
And we're going to then arrange by accuracy overall so that it's kind of sorted nicely. Next, we're going to produce the model summary by class. So we're going to take model summaries. We're going to select the model type, optimized, so what type of model it was, the data type, accuracy class, and accuracy overall. And we're going to unnest accuracy class. So accuracy class is a list of tibbles. By unnesting it, then it's going to basically repeat all the other values and glob it on. It's kind of funky. You have to play around with unnest a little bit I mean, it still kind of confuses me.
Yeah, it's messy.
Especially when you end up with like nested lists on lists. But really what we ended up here is this used to be one row, Bayes standard.
Yep.
And now it's repeated for 9 rows because our
9 pitch types.
9 pitch types there. And so with overall accuracy is also repeated 9 times. We're going to remove matches because that's not really important for us right now. And then we're going to glob together class actual and n to create a new column called pitch type and separate it with a space dash space. So this is so that we end up with these 2 rows globbed together in a nice format. We're going to pivot wider by pitch type, so then each column is actually going to be ch-1678. So that's change up. I have 1678n.
Yep.
So the number of times that pitch was potentially seen. And then the values are from within accuracy here, so that way we can view the performance by model by pitch type very easily. And then we're going to arrange by accuracy overall, just so that we can get a nice sorted model. Alrighty. So now we've got 2 final tibbles of evaluating all our models. Patrick, do you want to take us through this one?
Yep. Well, for our GT table, we've done this. We've done GT tables a number of times. But basically we loaded the GT package. This is an easy way to create some tables. We're simply going to first pass the GT function our data set. So that's going to get us off the ground with the most basic table you can have. No bells and whistles, no colors, just a simple black and white little table, obviously nothing rounded. And now we're going to make this kind of prettied up and a little bit more useful so that the information that we want pops. The first thing that we do is we're going to take column 4, which is accuracy, and we're going to turn it into a percentage, because obviously accuracy is the number of successes out of the total number of attempts. So we'll turn that one into a percentage, and then rows 5 through 7, the other rows, we're just going to say, hey, go ahead and round those to 2 decimal places, because whatever, it gets messy going out to 10 decimal places, and we probably aren't even convinced that we have that much precision in those numbers anyway. So let's go to 2 decimal places. Seems a little bit better. Next, we're going to add some coloring. If you were in Excel, this would be like hitting the conditional format button, and that's what we're going to do. So we're going to pass this function first the column that you're interested in coloring. So in this case, we're going to start with column 4, because why not go in order from left to right? We'll start with column 4. We're going to say colors, and we're going to use the scale package. We didn't implicitly load the scale package, so we're just going to do this little, hey, use the scales package, ... And this is the function that we want, which is color numeric, because obviously overall accuracy, actually all of these are numeric values, right? They're not discrete values. They're not classes. We're going to color them based on numeric values. The palette we're going to use is red, white to blue. So that's going to be like a low to high. And that's specified by the fact that domain equals 0 to 1. So there's our low to high, right? Because accuracy, again, is a percentage. So it's a probability residing between 0 and 1. Moving on, we're going to do the same thing for the other 3 columns for log loss, Brier score, and AUC. So obviously we pass those column numbers in there. We give the scale the same palette, and we set domain to equal null so that the previous column's information doesn't have an impact or influence the columns following it, right?
Yeah, that's why we also separated out data color. So we could have done data color 5 through 7.
We could have done all of them, yeah.
But that would impact, like, the coloring for then the Brier score or AUC would be based on log loss. Or like the way that the scaling of the coloring would work. We didn't want that, so that's why we broke it out into each individual column.
Right.
So let's run that now that we
run
have
this.
Oh, there we go. Colors.
There we go.
Colors. Pretty colors.
That's pretty cool. So the high. So obviously this is now arranged by overall accuracy. So total accuracy is at the top. The highest model at 76% hit rate was that random forest upsample data. And so again, if you watched episode 59, where we discussed the fundamentals of all these things, up and down sampling, and then our 4 measures of model comparison. We went over that in episode 59. But if you remember in episode 59, the example model that we used was this random forest model, and the upsampled model seemed to outperform the other models. And it does seem like we have a run of, what is that? 1, 2, 3, 4, a run of tree-based models. So XG Boost is also it's a boosted tree-based model.
Boosted.
Yeah, so we have a run of tree-based models before we get to anything else, before we get to that neural network. So it seems like this data, tree models do a good job of identifying or differentiating between the classes within this data on our test set. So let's see, what else can we pull out? There might be something off there. Log loss is NA for that top one, so we don't know.
I probably coded something up wrong,
we might have
honest.
to check. We might have to check something.
Look at my code. Hey, there's a kudos for you if you can find what I did wrong in my code.
Bonus points.
Bonus points. Extra star. Gold star for you.
But pretty interesting. It allows you to kind of go through and really, compare different models and see. We could have done this. We did this with a GT table. I kind of like GT tables. They're really nice and clean. We could have done this with a DT table, and that would have allowed us to like do some filtering and ordering and things. Either way, you just want to put together a table, especially when you have this many models that we built to help you kind of evaluate them and score them and understand how well they did. At the bottom, so the worst models. So what's down? Okay, so downsampled models, as we talked about in episode 59, the downsampled models, as you would expect, had a little bit more difficult time. And as I highlighted in episode 59, one of the limitations of a downsampled model is you're throwing away data, right? You're downsampling to the lowest observed class, which for us was, I think, knuckle curve,
which had like 200.
250.
It was right. Very, very small sample size.
So you throw away data, which effectively decreases the ability of the model to learn. And so then you go and apply it to a test set, and it says, wow, there's lots of values here that I've never seen before, or interactions between these values that I've never seen before, and I don't really know what to do with this, so I'm going to make my best guess based on what I have seen in the model that it was trained on. So the downsampled models tended to be, tended to have a much harder time. So that's a little bit of the overall accuracy. We can jump into the within class accuracy table, which was built in a similar manner, just obviously with a larger number of columns across the top, because we're identifying each of those 9 classes and how well we did.
Yep. So I'll just run this because we take GT, put in this wider data set here. We set the color to be from 4 all the way over, because in this case we do, like, they're all on the same scale. So I do want to have coloring impact each other, but I'm also setting the domain to be from 0 to 1. So I guess it actually won't be impacting each other. The colors, it'll be red when it's 0, blue when it's 1, and right, white in between at 50 or 0.5.
And we can do that here because these are all accuracy numbers. So again, they obey a probability distribution of being bounded at 0 and 1. Unlike log loss and Brier score, right? Like log loss, like a cross entropy, Brier score, like a mean squared error. Those values can exceed 1. So this wouldn't be appropriate if that were the case.
Exactly. And then we're going to throw a format % because also we don't really need to look that far down the decimal places. So by default it does 2. So we're going to do that. And now we're going to look at within or cross-class accuracy. All right, let me see if I can click zoom and make it show up prettier a little bit. There we go. All right, that's a little bit bigger. There we go. Yeah. Lots of pretty colors. And so what's kind of cool to look at here is all of these, like, immediately when you see all these, top performing models here, they all do really well on the same classes. There's like a pattern here where four-seam, we also kind of mentioned this earlier and we kept on bringing it up, but like the four-seam fastball, the change-up, the curveball, the slider, because the N was so high, we're assuming that the training and the test are relatively similar in this. They it's like cheating almost a little bit by default to predict one of those early on, because the probability of it being one of those is higher than like KC. KC, there's only 264 of them. The probability of it being a KC is lower. So it would be penalized basically for thinking that would happen more often.
Right. That's right.
But it's also interesting to kind of see, like, the way that, like, even within, like, XG caret upsampled, it starts getting pretty solid across them, but it then starts losing accuracy on, like, four-seam fastball. So it's like, there's always a bit of a trade-off. You don't get free cake.
And this might be an argument for some form of ensemble model where we're combining predictions, where maybe we like that the model some of those models at the top do well on the higher observed classes. But when it comes to the potential that it's one of the smaller classes, we might use predictions from the one of the other models that does better with those, or separating out the predictions, or combining predictions and weighting the models based on information, based on their success rates within these different classes. So lots of options there.
Yeah, I find it also very interesting for the random forest and XGBoost for both caret in the standard. So standard being like we didn't apply any special modeling to it. Caret meaning it tried to optimize. For the downsample, they're all kind of middle of the road. They're kind of generally predicting everything kind of bleh.
Bleh.
Bleh. But it's better than a coin flip. And this might, you might combine this with one of our high performing models on all the other classes to try to get an ensemble learning, whereas RF and XGBoost are by definition ensemble, but like we're adding additional models that are trained on different information to add more complexity to the model.
Yeah. I think that's the bottom, isn't it? Yeah.
Yep, this is the bottom here. Yeah. And then, our deep neural network didn't do so well, especially on the downsample data, which isn't too surprising because everyone's about, big data and, AI and all that. Well, the reason neural networks and stuff work is they need a lot of data to look at. They're looking for a lot. They need to be trained on a lot of data. They also need to see it a lot of times. The way that it learns is it looks at it a bunch of times. And in my algorithms, I didn't change the number of epochs, so the number of times it looked at the data. And so this was deep, meaning that it had a bunch of parameters it needed to be training on. Like it had it had 3 layers, 500 nodes.
500 each, yeah.
And so they're all densely connected. So there's a ton of different weights that it needed to be modifying, but I didn't change the number of times it saw the data. As well as it being a downsampled data set means that there's even less data for it to be training on.
Right.
It might have, like our neural networks might be suffering not from being just poor models, but the fact that we didn't let it look long enough.
Yeah, and that's the thing, right? At the end of each of those epochs is when the neural network is going to update its weights. So you had 3 internal nodes at 500. What did you have? 500.
3 hidden layers.
3 hidden layers with 500 nodes each. Yeah, that's what it was. So, at each of those epochs, it would look back and say like, "Ooh, okay, what can we learn now? Adjust some of these weights. What can we learn now?" So, if you don't give it enough kind of looks, maybe that's part of the issue here. The other thing I think that's always interesting to me is that, as complex as the neural network is, sometimes lots of complex models don't outperform these more simpler algorithms. Tree-based models are relatively intuitive and easy to explain to someone, and you can visualize the trees sometimes, and so it's interesting to see that the neural network, the more complex model, didn't solve the problem any better than some of the simpler models. I mean, the random forest is like, one of the easiest ones you can easiest ones you can run, and it did pretty darn good once we upsampled the data and showed it enough information about the different class types, right?
And let it optimize a bit.
And unoptimized it. And even the RF caret model, I mean, even the basic model without upsampled data was still, was still competitive.
Yeah, I mean, it only lost to our best model that we trained. It only lost by 0.45 accuracy.
Right.
Which then you have to make the call. I mean, we now have this model, so now we have it trained. But in the future, you're like, well, we know that upsampling, it helps. Clearly, it's our best model. But of our top, 10 or so, basically all of them are just on the standard data set. So maybe upsampling doesn't give us
it didn't
the
give us
boost
any
that
more
we
information.
were expecting.
Yeah, which is also the other thing, there's also some considerations to make, like, this was obviously a fun little example, but if we were to like productionalize this, we're also not just thinking about, the accuracy and the log loss and the Breyer score and how good the models are. We're also thinking about how good is the model relative to the computing time. Because if we have to productionalize it, we might even use a model that isn't the best performing model, but is good enough and has a quick amount of
Response, right?
Yeah, response time, right? It doesn't take a ton. There's not a huge, there's not a lot of heavy lifting to get it off the ground, and so there's a lot of things that kind of go into not just building and comparing the models, but then thinking about how they're going to be used in the real world for domain experts to make decisions.
Yep.
And sometimes that information has to come in really quickly, in which case, PitchFX data is probably not a good example of data that needs to come in really quickly, but in which case you are sometimes okay with saying we'll sacrifice a tad bit of accuracy for the in an effort to get the response quicker because we need it quicker,
Yeah.
right?
Yeah, there's things to consider outside of just the model itself, which is why we have jobs.
Yeah, no, that's right. Yeah. There's humans on the other end.
Exactly. So with that, I think we can actually put a fork in this entire series. PitchFX, ML, all this fun stuff. I had a great time working on this. This is stuff that I didn't get to work on a ton of. So this is really interesting for me, and I got to learn some new stuff, like dealing with large files, putting into Git, so that we could share all of this with you, so you also don't have to wait 5 hours to run all these models.
Exactly.
We're going to post it all on GitHub.
Now we need to think of our next series, though.
Yes. Post comments on github.com/thebioengineer/TidyX. Post issues there for us to see what content you'd like to see in the future. Put comments down below. Tell us, email us, Twitter us, all the different things. We almost have 1,000 subscribers here on YouTube. So thank you all so much for joining us for 60 episodes now of TidyX.
Incredible.
Thank you all so much. As always, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ford. You can find me on Twitter at OSPPatrick. And you can find this screencast on Twitter at Tidy_explained. Or if you prefer not to put it out there for the public to see, you can email us at tidy.explained@gmail.com. As Ellis said, open an issue on the GitHub repo if there's something you want to see in the future, or potentially a series that you'd like us to do. Or you can always like, subscribe, and comment on the YouTube channel. That is another great way to share your thoughts.
All right. Thank you all so much, and keep on exploring your world. Bye-bye.